Okay, today we are going to make our neural nets run on GPUs. First off, I will have you go to, I'm going to link this video in the description, but for anyone using Windows, this guy goes through how to set up your system to use CUDA in VS Code. And so I'll let you go to that video, see that, because yeah, honestly that part's kind of difficult for me. I don't want to go through all that. This is an hour-long video that he has. I think he probably might be able to stop like within 35 minutes, but probably also depends. It's been a long time since I've done this, so there's that. You'll make this cmake list.txt folder. Everything should be, I guess, path dependent. This will be path dependent. It might be the same, I don't remember. But you'll have those two things. This should depend on what GPU you have. But yeah, go through that video first, then come back here. So we got the cmake list.txt file. Got this windows.bat file as well. You can copy that, copy this in here. I'm going to use this terminal. We're in the GPU stuff. So in your command prompt, go all the way to this GPU stuff. GPU stuff was a new folder I just made. But wherever you're making this stuff, create a new folder called GPU stuff, go into it, and then code dot to open up your VS Code. Add these two things in there. I'm going to test this out by adding in something I've already made. But let's see. So first, do the O1, do that. Once that's done, it should create this build file. Interesting. Let's see if that went back up a level. Still. So if I go back up a level, okay, let's get rid of that. I'm going to save this and F7. So I'm doing AMD 64. What is that going to do? Let's find out. go over here to build. Ha. Debug is right here. We will be needing that. Let's see, what did I... matmul cu. So I think it'll be a matmul.exe, but let's see what we got here. Main.exe. Let me see if that's the same here. Yeah, okay. I don't remember how to set that, but it'll be main.exe. So we'll go cd into build debug main.exe. It says yupper because shows that there is a device. Okay, still going through. And it worked. Okay, so go ahead and okay, so we'll keep this. Get rid of that. Get rid of all this. And we'll come back and do it again. So first off, we're gonna have a go back to my references here. Alright, so you need global before your kernel function. Void matmul float star destination. I'll finish this up here in a second. But okay, some of the things that you'll need are int m. Let's do arrows equals 4, comma b a calls equals 3. Does that work? Yeah. B rows equals, why don't I just do this? 3, comma b calls is 2. What was that? 3. And 4. Okay, so that gets the dimensions of our matrix. Let's see. I am unprepared at the moment. Give me one moment. Okay, where's the original stuff? Alright, we'll just wing it. Okay, first thing we need is float star A equals malloc. We'll do A rows times B, A calls times size of float. For some reason it keeps wanting to do a float 1. I have no idea why. Oh yeah, you need to make this converted into float. B rows times B calls times size of float. And then float star dst pointer to a float. Why are these weird? Size of float, malloc. Let's go back to where. Oh, okay. Float star. And we'll do it one more time. Star malloc. You can skip this step if you just do what I'll do in the future and point yourself or include in here just I guess the issue here would be if you go all the way into GPU stuff, then you can't really access. Oh, you can. You can do hashtag include what's it called? Back and then go to matrix ops. Matrix ops dot cpp. Actually, yeah, I think that'll work. This might need to be a CU file. I'm not sure. Let's try it. T equals matmul. That's fine. We'll do A rows comma, B calls. Okay, so if that works so far, we'll save this. Do an F7. See if it worked for that. So F7 works on this cmakelist.txt. And then we'll just go over here and do it worked. Question mark. Okay, so save again. F7 again. Wait for that. Go over here to terminal. And it's already in build debug. Do main, executable, it worked. Okay, cool. So yeah, you can just do matmul with all these. Which I probably should. You know, let's do that. Mat A equals mat alloc allocate A rows, comma B A calls, and mat B equals mat alloc B rows, comma B calls. Alright. Give me 1 minute to reheat my coffee. Okay. We got that. And next, let's see. We can first of all mat fill A with 1 F, mat fill B with 2.f, and then we're gonna make some device pointers. Float star d underscore a. We're gonna copy the data from the A matrix into this. Which this itself will actually just be a pointer to a place in the device memory. So we'll actually be copying A into the device with this pointer pointing to that device memory. Star D underscore B, star D underscore DST. Is that right? Yes. Okay, cool. Create those. We're going to allocate memory again, except here we allocated memory in host, which is the CPU. Well, really the RAM for the CPU. And then we're going to allocate next memory for the GPU, which actually don't remember if that's still on the RAM or if that goes into the GPU. I will have to research that. But cuda, malloc, not 3D. You reference DA. You need the ampersand because you're going to need the address of this, and you'll be putting information into the address of this. And you're going to be doing it with a row. You're going to allocate a rows times a calls times size of float. Just like I had started to before. Just allocating memory. Exactly the same. And D. Just cuda has a function for it. B rows times B calls times size of float. And then next is to mem copy the memory from a.es, or a.data is what we have it as. So a.data was the address of our memory, of our matrix memory. So you copy that, my bad, D underscore A. So this destination first, then the source. So copy that to here. And what you're copying is a.data, and then you need the size again. A rows times a calls times size of float. You can definitely just create a size being a rows times a calls times size of float. But yeah, I'm just gonna type it out. Then the last thing you need, cuda mem copy host to device, because we're transferring from the host to the device, and then later we will be transferring from the device to the host. D underscore B data B rows times B calls cuda mem copy times size of float, and then we're copying from the host to the device. After that, well, next is when you use your matmul. Next part is we're gonna do the dimensions of the block and the grid, and then we'll launch the kernel. 2, 3. A lot of this you should understand from seeing the CUDA crash course by Elliot Arledge. But we'll do block dim. Basically always 32 by 32 is what we'd use. And just kind of reminder, the blocks are a little piece of the grid, so you could imagine each one of these hashtags or whatever the symbol is called as a block inside this whole thing as a grid. And each block has 32 by 32 threads. Each warp has 32 threads, so this block would have 32 warps. It would be a square of that. We'll do dim 3 grid dim, which we will make as the dimensions of our destination matrix here, divided by our block dimension. Let's see, dst.calls plus block size. Let's see, block size is what I had. So block size is what is going to be 32. We'll just do up here int block size equals, I need to start getting used to this, 32. So make that. So this will be that there divided by block size. And what this will do is, like, let's say the columns is only 5. Well, we need at least 1 for the grid dimension. So 5 plus block size makes it 37 minus 1, 36 over block size rounds to 1. Rounds down to 1. This minus 1 is because if you have block, so 32, if this is 32, this would be 32 plus 32 is 64. But if you have exactly 32 here, you only need 1. 32, 32, 64 would make 2. Minus 1 would round down to 1. So that's that one. Comma dst dot rows plus block size minus 1 need the parentheses on there divided by block size. So that gets us our dimensions. And this is just for the most naive matrix multiplication. We're gonna do matmul. Need 3 brackets. And then you do block dim grid dim 1, 2, 3, followed by the arguments, which we have not set up here. DST float star a float star b. We'll need int a rows, int, let's see, dst rows int dst calls and int a calls, which is equal to b rows. Those are the 3 dimensions we'll have to go over, equivalent to the 4 dimensions of the of our 3 different matrices. Okay, so we have d underscore dst underscore a, d underscore b, dst rows, or we could do a rows, b calls, a calls, or you could do dst dot rows, dst dot calls, and a calls. Yep. And then where am I at? Okay. Up here, we're gonna make, as it goes across the threads of the, let's see, we're gonna spread across the threads that we have allocated through here. Each row and each column is gonna get its own thread. Each row and column of the destination is gonna get its own thread, and each thread is going to run through the calculation, the here, I can probably show this more visually. Let's see. There we go. Can never remember which one it is. Okay, so x, 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 x. Okay, so we got a 3 by 2. We'll have a 2. Let's see, 3 by 2. We'll have a 2 by 1, and we'll have an output of 3 by 1, which is x, x, x. So this is A, this is B, and this is C. What we're going to do is we're going to, each thread is going to calculate for each one of these. And so to calculate this, you're going to take this combined with this. So we're going to loop over, for this one, we're going to loop over the, what is that? The columns of A, which is equal to the rows of B. So each single thread is going to do that, a certain spot, go through the columns of A, which is equal to the rows of B in a for loop. But first, yeah, we'll have the thread row, which is the block index dot y times block dim dot y. Okay, so block, remember the grid, let's see. We'll show the grid like this. So this is going to be our grid of our threads. We'll pretend each one of these is a block. Each X is a block. So block 0, block 1, block 2, block 3, block 4. Laid out in a 2D grid. Each block has threads within it, 32 by 32 for each block. And so block index says in the y direction, are we at the 0th? Basically which row of the block. Like, are we at the 0th row of the block, first row of the block, second row of the block? Block dimension dot y is going back down here to block dim. This is the x and this is the y. Made them both 32, so they're the same. But in order to get to like the first thread of this block, we have to go through all the threads in here. So 32, 64, 96, go through 96 to get to the first thread here. So this row is block index times block dimension dot y plus thread index dot y. We also have the column, which is block index dot x times block dim dot x plus thread index dot x. We'll have a checker to make sure that row is less than dst rows, and call is less than dst calls. Take that. So that way only, like, you're not trying to access memory out of bounds, basically. The ones that don't do this, they're just gonna, the threads that are beyond this or this are just gonna do nothing. And we'll have a float sum, which will equal 0.f. Do a for loop, which will go up to a calls, and we'll have sum plus equal. So this sum variable will be local to each and every thread. So each one of, when we had the a times b equals, what was it? This was the destination one. There was an a, there was a b, and now there's the destination one. Each one of these has its own sum variable, and it is going to be a row times k. Let's see, sorry, no. My variables over in the other one's different. Row times, let's see, that was a calls plus I times b, let's see, what is it, I times a calls plus, is that right? No. This would be dst calls plus, I think it's call. Yeah, that's what it is. So a is going across. So for each row in the destination is each going to have a sum. Sum is going to add in going through the i's, which if you're on the 0th row, 0 times a calls would be 0. Go through the i's of that first row. Whereas b is going to go down down the rows here. In this column. So I times the number of columns in the destination makes you jump from 0 times the number of columns right here. Then 1 times the number of columns. This is the number of columns. 0, 1, 2. Or, so there's 3. 3 times 1 drops you down here to here. Plus call, which is a separate thing of threads. Or like is another reference point to your thread. If you're on 0 row, 0 call, so like you're this guy in the destination, you'll go through your first row of your A matrix, first column of your B matrix to get this first sum. And then the next thread is going to be a different column and thread below will be a different row. Hopefully that makes sense. But then you do, then you do DST row times DST calls plus call will equal sum. And I think that this way would be faster than accessing the DST right away and doing DST with these plus equal all of this. Unsure, but I feel like putting some in here would be a little faster rather than going up to the GPU memory, the higher levels of memory to find these guys. Not totally sure, but yeah. Let's see, so there's that, and that's it for the kernel itself. That will store all the calculations into DST, and then after that we just have to, we stored it all in the device DST, the device destination. So now what we got to do is cuda memcopy from that to the host, which the host is dst.data. That's the destination. The source is d_dst. We need the size, which is dst.rows times dst.calls times size of float. And then up here we were copying host to device. Got to tell it copy from device to host. And then after that, all we gotta do is delete our extra unneeded memory, which is DST, DB, and DA, which cuda has a thing for that. Cuda free d underscore, we'll go with a cuda free d underscore b and cuda free d underscore dst. But we could go down here and mat print dst let's see, made it 4x3, 3x2, so destination should be a 4x2. Save that, hit F7, Does it work? Exit with code 0, that's good. Go over here to terminal, cd, if you're not already in the build, debug main.exe. Before I do that, uninitialized local variable dst. Oh, did I uninitialized? I do need to allocate memory for that. Cuda malloc and d under dst, and that'll be ds a rows times b calls times size of float. There. Should get rid of this. Oh yeah, gotta save and F7 it. So if you tried it before I did, it would not have worked properly. Okay, go back here, hit enter. And it gives you what it should be. 1s and 2s of a 4x3 and 3x2, so it'd be 1 3 times times 2 3 different times, so 2 plus 2 plus 2 is 6. These will all be 6 in a 4x2, and that's our first one. It's our first video. We'll add in things like, well, this is just a regular mat dot. We're going to also add in the bias, add in different activation functions. ReLU is super easy. And then we're also going to work through more efficient or faster matrix multiplications, and then clumping them together to get the full image neural net. But I'll see you in the next video.